that we've finished up some basics on probability, we're going to start to look at probability distributions. First, a definition. A random variable x represents a value associated with each outcome of a probability experiment. The word random indicates that x is determined by chance. You should be able to tell if a random variable is discrete or continuous. Discrete is going to mean it has a finite number of possible outcomes and they can be listed. Whereas if a random variable is continuous, it will have an infinite number of possible outcomes. And the best way to explain this is through an example. So in example 1, it says determine whether each random variable is discrete or continuous and explain why. So number 1 says let X represent the number of Fortune 500 companies that lost money last year. In case you aren't aware of it, when we say Fortune 500, we really do mean a listing of 500 companies. So if X is going to be the number of companies that lost money last year, think about what values X could take on. So for instance, maybe none of them lost money, or maybe one lost money, or maybe two of them lost money, or three. And since there's 500 companies on the list, I could keep going and list 499 and 500 companies as possible values for X. So I was able to make a list, and there's a finite number, meaning it doesn't go on and on forever. I can count up how many objects are in this set. So therefore, this is a discrete variable. In number 2, it says let X represent the gallons of gas in a 21-gallon gas tank. Now, in this situation, I can't exactly list the number of gallons that might be in that gas tank. Because, I mean, sure, there could be none. And, okay, yeah, there could be 1 gallon. But also there could be a portion of a gallon. Maybe there's only half a gallon. Maybe there's a quarter of a gallon. Maybe there's a third of a gallon. There's going to be an infinite number of values that X can take on. You know, maybe it's 19.5. Maybe it's 19.555. Maybe it's 19.555555555. I know it's going to be values between 0 and 21, but it is not possible for me to list them. So this is an example of a continuous random variable. So that's the basic difference between those two. Now, in this section, we're going to focus on discrete probability distribution. So these are going to be things where we can list the different possible outcomes. And when we assign those a probability and list them all, that's what we call a discrete probability distribution. Discrete probability distributions must satisfy these conditions. The probability of each value of the discrete random variable has to be between 0 and 1 inclusive, meaning including 0 and including 1. And the sum of all the probabilities has to be 1. So in examples 3 and 4 here, I kind of combined them. It says determine whether each distribution is a probability distribution. Explain your reasoning. So first of all, the first one says this is days of rain and their probabilities. X is a discrete variable because you can see it only takes on 4 different values and I can list them. Now I need to check the 2 conditions to see if this is a probability distribution. So first of all, I check each of the numbers and make sure they're between 0 and 1, and they are. Next, I need to add up all these numbers and see what I get. So if you add up 0.216, 0.432, 0.288, and 0.064, you will get a total of 1. So therefore, this one is a probability distribution. Since both conditions are met, this is a probability distribution. Now in example 2, they haven't told us specifically what X is measuring, but again, we can tell it's discrete because it takes on only the values 5, 6, 7, and 8, and we can count those up, we can list them, so therefore X is a discrete variable. Once again, we begin by checking the 2 conditions. First of all, that all the probabilities are between 0 and 1, and you can see that, again, they are. Next, I'm going to total up these probabilities and see what I get. you're going to get 1.07. And since that is bigger than 1, this will not be a probability distribution. Because remember, 1 represents 100%, which should be all the possible things that can happen. If my probabilities total 1.07, I'm saying that 107% is the total of all the things that can happen. And I went and used some notation here just to make the sentence shorter. It says, since the sum of the probabilities does not equal 1, this is not a probability distribution. And now taking a look at the third example, again, we can see that x is a discrete random variable, happens to take on the values 1, 2, 3, and 4. And we begin by checking condition 1, that all the probabilities are between 0 and 1. 1/2 and 1/4 certainly are, but 5/4 is equivalent to 1.25. That's not between 0 and 1. So right there, I know this is not a probability distribution. But also notice we have a -1. Probabilities don't take on negative values. So that's another reason why this would not be a probability distribution. So I can say, since the probability of 3 happening is not between 0 and 1 inclusive, this is not a probability distribution. So now that we know how to identify probability distributions, we're ready to actually create them. So I modified again example 2 just in terms of how the table here is displayed. In this example, we have an industrial psychologist who administered a personality inventory test for passive-aggressive traits to 150 employees. Each individual was given a whole number score from 1, extremely passive, to 5, extremely aggressive. The results are shown in the table below. Construct a probability distribution for the random variable x, then graph the distribution using a histogram. So x is representing the score they got on the scale. And notice, it's only possible to get 1, 2, 3, 4, or 5. You can't get 1.5, you can't get 1.12. So therefore, we know that this is going to be a discrete variable. And we are now going to construct the probability distribution. So what that means is I'm going to be calculating and completing a table that shows the score, and then next to it is going to show the probability of that outcome occurring. Now, to calculate these probabilities, to find, for example, the probability if a person was randomly selected that they received an extremely passive rating, to do that, I'm going to take the number of people who did get that rating, their frequency, which is 24, and I'm going to make it a fraction out of, because remember, probabilities need to be fractions, out of the total of the sample, which was 150 employees. And if you take 24 and divide it by 150, you will get 0.16. Now, to calculate what P of 2 is, do the same thing, except take the frequency of 2, which is 33, and divide it by 150, and continue down the table. These are the values you should get for the probability of 3, 4, and 5. And to check and make sure this is a probability distribution, again, we're going to make sure each probability is somewhere between 0 and 1, which they are. And we're going to total up these probabilities. And if we add all the probabilities up, we do get a sum of the probabilities equal to 1. Therefore, this is a probability distribution. So we've completed the first task. Now, to graph it using a histogram, I would expect you to use Excel. Now I've gone into Excel and I have entered my probability distribution. Now what you're going to want to do is highlight only the probability column, including its heading. Choose Insert, go over to your charts, and under the first icon, you want the very first choice under 2D column. When you choose that, again, you've got a bar graph and not a histogram because these bars have gaps between them. I'm going to go ahead and click on the bars, And then in the Format Data Series window, click on the three bars and eliminate the gap width. And then the other thing I might want to do while I have the bars highlighted is go back to the paint can, open up the border portion, and put a solid line border on here. And again, you can change the color to make it visible. Now you can see the bars. So I'm going to go ahead and put on titles and labels by clicking inside the chart area, going to Chart Design, and adding chart elements. You've seen how to do this in other videos. You can see I've added some titles and labels, which is important. But there's one additional thing to note here, and that is these labels 1, 2, 3, 4, and 5 across the bottom are actually the default. In no way did it actually see what I had over here in this X column and set it up according to that. And I'll prove that to you. I'm just going to change these numbers up. I'm going to make it 0, 1, 2, 3, and 4. So suppose instead that these were my X's where the default does not match. What you would do in that instance is you would click on your chart, go to Chart Design, and you can see there's a Select Data icon. You would choose Select Data, and down towards the bottom of the window, it says Horizontal Category Access Labels. And then there's this little icon in the right. If you pick that icon, you can now go and highlight just the labels you want applied. Don't include the X heading. Once I hit return, it'll take me back to the window. I can hit OK. And you'll notice it did change the labels across the bottom. So if you do need to adjust those, that's how you do that. Now, one thing you should be able to do for any kind of probability distribution is calculate the mean, the variance, and the standard deviation. So we're going to do that for the personal inventory test data. So the same data set we were just working with. This, by the way, is examples 5 and 6 in your book. And all you need to begin is the actual probability distribution, which we found in the last problem. First of all, to calculate the mean, and we have the population mean symbol here because, again, this probability distribution represents everything that can happen. We're supposed to take the sum of each individual score times its probability. And we usually do this by setting up a table. So I've gotten my table set up, and I'm going to put a column next to it for X times P of X. And I'm going to get the values for this column by taking the X, in this case 1, and multiplying it by its probability, 0.16. 1 times 0.16 is, of course, just 0.16. I'm going to do the same thing for each of the other rows. Multiply the score by its probability. Now, one thing to notice here is this mean formula, notice there's no dividing by anything at the end. You are finished when you have the sum of the X times P of X column. So be careful here and don't just kind of do what you're used to doing. Probability distributions are a little bit different. So if you sum up this column here, you get 2.94. But remember, as far as rounding goes, we're going to round to 1 decimal place beyond what was given originally. And the rankings had 0 decimal places, so I'm going to give 1 decimal place. Now notice we got a mean of 2.9, which is not actually a score that could be reported. So when we interpret this, we would want to say the average score was, and the closest whole number is 3. So the average score was close to 3. The average score was close to 3, meaning on average, employees are in the middle of the scale. So that's how we calculate the mean. Now, once again, for variance and standard deviation, you're used to formulas that have a division step in them. But again, these are probability distributions which work a little bit differently. There are some similarities to it as well, though. So first we're going to go about calculating the variance. And in order to calculate the variance, you'll notice you have to take each individual score, subtract the mean, which we just found, square those, multiply that by the probability of each score happening, and then add everything up. So I'm going to create a table for that. So I've got my table started. Now the first column I need is a place to subtract the mean from each score. Then I'm going to need to square the values in that column. And finally, the last step according to the formula is then to take that column and multiply it times the probability, and then I'll sum up that last column. Make sure you use all decimal places of your mean, and notice you're going back to x, not p of x, and subtracting the mean. So I'm going to do 1, take away 2.94 to get negative 1.94. I do 2, take away 2.94, and I continue doing that down this column. Now I'm going to take these values and I'm going to square them all. So if I take, and again, be careful with that negative sign, put it in parentheses if you're using a calculator. I'm going to square negative 1.94, giving me 3.7636. Continue squaring all the rest of the values. I have now squared the values, and the last step is to take and multiply by the probability column. So when you're doing this step, make sure you're looking here and here, multiplying those two numbers together, and that'll give you the value for the last column. All right, so I have my last column, and the last step, if you look at the variance formula, after you have managed to calculate all of this, is to add up all of those decimals. So if we take the sum of x minus the mean squared times the probability of x, we're going to add up all of these decimals here, and you're going to get about 1.6164, and that's going to be your variance, which again is this symbol here, sigma squared, and report that value to one decimal place, so 1.6. That's a measure of how spread out this data is. But again, a better measure of it is one that is in the same units as the original, and that's found by calculating the standard deviation. Now, just like you're used to, according to the standard deviation formula, you're going to take this, which is the variance, and just take the square root. So again, when you're doing this though, please make sure you go back to using all the decimal places of your variance. So we're actually taking the square root of 1.6164, which is going to be approximately 1.3. So again, in a lot of ways, it's similar to how we did standard deviation before, but make sure you're following the correct formulas for the probability distribution.